All right, so in chapter 7.1.3, we are going to be doing another section on related rates, but this time with similar triangles. So in this problem, we have Eric, who is 5 feet tall, is walking away from a 16-foot lamppost at a constant rate of 4 feet per second. We've got our lamppost, we've got our guy. I'm going to be drawing a triangle below. We're going to make a prediction. As Eric walks, his shadow is growing longer. So if you ever walked away from a light source, your shadow will end up growing the farther you are away from that lamppost. So the rate in which it grows, do you think that it grows at an increasing rate, a decreasing rate, or a constant rate? And I'm going to go ahead and pause the video to let you think about your answer. Well, it turns out they're going to be growing at a constant rate because of similar triangles. You end up having a similar triangle problem here, where I'll just draw it below. So the triangle that we have is our 16-foot lamppost, our 5-foot guy, Eric, and we have two distances. We have an x and we have an s. X, it represents the distance from him to the lamppost, and s represents the length of the shadow. These are actually going to grow at a constant rate because we have similar triangles, and we'll see why that is in just a second. We want to calculate his rate that his shadow is growing when he's 30 feet away from the lamppost. So we have a situation where we know, want to know, and a snapshot. We know his when he's 30 feet away. Well, that's our snapshot. That's what snapshot is. X, our distance, is when he's 30. So he's 30 feet away. And we know that he is moving at a constant rate of 4 feet per second. So what is changing at a constant rate of 4 feet per second? It's his distance away from the lamppost, which means we could say this is dx dt, and that is going to be 4 feet per second. We want to know how fast his shadow is growing, so his shadow, which is ds dt, and that's what we're solving for. So it may seem like we have a similar problem to the previous Pythagorean theorem problem. However, it's going to be a little bit different this time because we have similar triangles. And similar triangles, if you remember from geometry, we can have 16 over, so our entire thing, which is 16 over x plus s, equals our smaller triangle, which is 5 over s. So if that's our equation we're going to start with, let's go ahead and get the variables out of the denominator by cross-multiplying. It's kind of unfortunate that 5s look like s's, but bear with me here. So 16s equals 5x plus 5s. Now, since we are solving this problem, we are looking for the dx and ds, so let's go ahead and take the derivative of everything. So d over dt with respect to time. And we'll fill in each of these. Of course, as I'm writing this, please feel free to pause at any time to go ahead and try this yourself before I just do it. So let's take the derivative of, actually, before we do this, I forgot one step here. I jumped ahead of myself. We have 5s and we have 16s. Let's go ahead and subtract the 5s onto both sides. So this actually becomes 11. So now let's take the derivative. The derivative of 11s is going to be 11 ds dt, and the derivative of 5x is going to be 5 dx dt. We are trying to solve for ds dt, so let's go ahead and divide both sides by 11. And we are going to plug in our dx dt because we know that, so that's going to be 4 feet per second. So 4, and 11. So we end up getting 20 divided by 11, which is going to be 1.81, and our units is going to be feet per second. So that is how fast his shadow is growing when we are at 30 feet. Now, here's the problem here. We didn't use 30 anywhere in our problem. So why not? In our derivative situation, our time when we can plug in our units, there was no place for me to plug in x is 30, because notice that in our original problem, our x ended up turning into dx dt. So when we scroll back up to the problem here, when he's 30 feet away from the lamppost, it ends up also being 10 feet away from the lamppost, the second one. Calculate the rate of Eric's shadow when he's 10 feet. Both of these are going to have the same rate because it is a similar triangles problem. And it doesn't matter where he is, the shadow is going to be growing at a constant rate, which is what our problem was answering right in the beginning. So that's why this problem is going to be a little bit different than our guy falling off of our ladder. And it's useful for us to recognize when we have a situation of Pythagorean theorem or we just have a proportions problem. Okay, so let's move on to our next problem. Our next problem here has a storage tank, and this storage tank has a shape of a cone. It says that it's 20 feet deep and 40 feet in diameter, as shown in this diagram. We want to make a prediction. Assuming that this tank is empty, as water is pumped into the tank, the depth of the water increases. If water is pumped into a constant rate, will the rate that the depth increases also be constant? So if water is constantly filling in, will our height, basically, the rate, the depth of the water be constant? No, because there's more water would take to fill up out here than there would be down here. So it is not going to be a constant rate. It's going to fill up, it's filling up at a constant rate. However, the height is going to be filling up at a slower rate. So let's go ahead and talk about what's going on. I'm going to go ahead and write down our cone here as, I'm going to split this in half because just like the previous problem, we had a triangle, right? So we have a triangle and we've got our water here. This is our water rising. And we have some rates where we are trying to solve for our depth. So we want to talk about our depth, which is our height, and the height is going to be represented as a rate. So that's going to be dh dt. The other information that we have here is our volume, because our volume is being filled up here. So we have dv dt. And let's go ahead and fill in our snapshots because we're going to solve a problem here. So we have a know, we have a want to know, and we have a snapshot. And then let's go ahead and talk about our volume. So we know that the volume of a cube or cylinder is going to be 1/3 pi r squared times height. The problem here is that we have two variables, and if we have two variables, given the fact that I have these two pieces of information, is not going to help us out. We don't want to have two variables. We want to have just one. So how can we look at our original problem looking at 40 and 20? Well, 40 is our diameter, so our radius is 20. And if we have a triangle where our 20 is here and our 20 is here, our radius is actually equal to our height, which means that I could simplify this problem. I don't want radius. I want this to say 1/3 pi h cubed, because this becomes h squared. So we end up getting 3 h's, which is h cubed. So let's go ahead and take this volume equation. So let's take the derivative because we want to write this in terms of rates. So d dt, d dt, and we will say dv and 1/3 pi h cubed. So the derivative of v is dv dt. The derivative of 1/3 pi h cubed is going to be the 3 is going to go out and it's going to multiply with the 1/3, so we're going to cancel out there. So we just have pi h squared. Then the derivative of h is going to be dh dt. And let's talk about the information that we know, because this is going to be our equation that we're going to use. So we have information on letter C that says that water is being pumped into a constant rate of 100 gallons per minute. So we have 100 gallons per minute. That's going to be our dV dt. However, we don't want gallons because gallons is not in our problem. Luckily, they tell us that gallons is that many feet. And 100 gallons, we're going to take this because 1 gallon is that many feet, so we're just going to multiply this by 100. So really, we end up having 13.3. I don't know why they give us that many different decimals. I'm not going to use all those decimals. Feet per minute. And we are going to, water is being pumped into the empty tank at 100 gallons per minute. How fast is the depth? So we want to solve for our dH dt, which is how fast our depth is rising. And after 10 minutes, so our snapshot is 10 minutes. We don't have a place to put minutes, so we're going to have to convert this into how much volume we're going to get. So let's go ahead and figure out. We're going to use, or we're getting 100 gallons per minute. So that's how many we are getting per minute, which means we can just multiply this by 10 in order to get our volume because we're getting that much feet per minute. So this becomes 10 minutes. We'll have 133.68 feet of volume, cubic feet, I guess. And we're going to use that. So let's go ahead and solve for our dH dt, because that's what we want. So we have dV dt divided by pi h squared. So that is our dH dt. We have our dV dt, which is over here, so we can plug that number in. So we have 13.368. Divided by pi. We don't have our h squared, so we're going to have to figure out how much our height is when we are given this much volume. So let's go ahead and look back at our equation here. And we know that our volume is 100, I'll do this in a different color, 133.68 equals 1/3 pi h cubed. So we are solving for our h. So we are doing the cube root of 133.68 divided by pi times 3. And that is going to be 5.035 approximately feet. So we'll plug that in for here, 5.035 squared. And that's going to be our dH dt. I'm just kind of rushing because I know I'm running low on time here, so I'm just going to tell us our answer, which is 0.1678 feet per minute. That is the rate in which our height is increasing at exactly 10 minutes when we are getting 100 gallons per minute filled up into our cone. All right. And here is going to be the assignment that you're going to do today. Make sure to tune in tomorrow if you have any questions.